This is the Mathematics Education Podcast from mathedpodcast.com. Welcome to the Math Ed Podcast. My name is Sam Otten from the University of Missouri, and today I am joined by Sarah Bleiler, who's an assistant professor of mathematics education in the Department of Mathematical Sciences at Middle Tennessee State University. Sarah, thanks for being here.
Thank you for having me.
We're going to be talking about Sarah's article in the Journal of Mathematics Teacher Education entitled Providing Written Feedback on Students' Mathematical Arguments, Proof Validations of Prospective Secondary Mathematics Teachers. That article is available online right now at JMTE's website and also be coming in print very soon. But Sarah, before we get to that article, I actually want to step back and ask you about your dissertation research, because I know that was a little bit different than this article, so I'm curious about your dissertation as well.
Mm-hmm. So I did my graduate student work at University of South Florida, and there I worked under Gladys Kersaint. She was my major professor, and also I worked closely under Denise Thompson, who's a co-author on this manuscript. And so for my dissertation research, I was very interested in the process of collaboration between mathematicians and math educators.
Oh.
When you think about the field of mathematics teacher education, there are a lot of suggestions out there in the literature that these two groups come together to better integrate math teacher preparation. And a lot of the focus in the literature has been on the products that have come out of those collaborations. Mm-hmm. And so I was really interested in looking more in depth at the process of collaboration. So I investigated a team teaching collaboration between a mathematician and a math educator. So they were working together to team teach a content course, geometry, for pre-service teachers, and a teaching high school mathematics course, methods course for teachers. So, yeah, that was kind of interesting, and I took a phenomenological approach in that study and really looked at how the instructors perceived their experiences collaborating with one another. And I used situated learning theory and the idea of communities of practice to think about how each of the instructors was perceiving their experiences based on how they view themselves as either a member of the mathematics community or a member of the math education community.
Wow. Yeah, that's a very unique kind of study, and I imagine a lot of interesting things came out of that. And you were doing the work in geometry content, but also methods, so you're kind of getting the different arenas as well and seeing how they co-taught with that.
That's right, yeah. And it was really interesting to see how each of them, when they stepped into the other's world, right, whether it be the mathematician in the methods course or the math educator in the content course, how they sort of interacted and were able to really develop themselves professionally and reflect on their own practices based on sort of joining that other community.
Mm-hmm. So the article in JMTE, that is also from prospective secondary mathematics teachers, so you are in the kind of teacher education realm, generally speaking. And you mentioned that was co-authored with Denise Thompson. I wanted to give you a chance to mention the other co-author as well.
Yes, and also a mathematician that we worked with, Mile Krajewski.
Okay, great. So help us follow you from your dissertation interests to this article. What was it that led you to be interested in proof or prospective teachers work with proofs and arguments?
Yeah, so a lot of it is the same reason that I was interested in my dissertation research. And I think back to my own experiences, particularly as an undergraduate in mathematics. And in my K-12 experience in school, I saw mathematics in a way that's very similar to how a lot of my students now are viewing mathematics coming into the university, and that is really seeing it as computationally focused and very procedurally focused. And coming into a study of mathematics at the university level, of course, that's what I expected math to be. And once I started experiencing undergraduate upper-level mathematics and sort of more of the theory and proof-based ideas behind that, it was kind of somewhat disturbing to me personally, because I thought, well, I had this view of what math was all of these years, and now that's sort of being flipped on its head, you know. So I am very interested in that transition period from the lower level of undergraduate into the upper level of undergraduate study and really moving toward that theory-based mathematics. And so a key part of that is students' ability to write and validate and read mathematical proofs. So that's really how I became interested in that topic. This particular study actually arose from a project that I developed in my qualitative research course at USF while I was studying as a doctoral student. So I designed the instructional sequence that I'll talk a little bit more about in that course. And then it just sort of progressed from there. I started working with Denise and with Bleiler, and we put together this study and started implementing it over the years while I was there.
Yeah, I think that's the hope of a lot of qualitative methods courses, that
yes.
when you design it, that it actually will come to fruition and become an actual, now published work. And I wanted to comment, too, on that transition from kind of the lower undergrad mathematics to upper. That was definitely resonant with my experience, because I also viewed math as very procedural, computational, and I liked it, so I was going further into math. And then I took a proof course, and then from then on it was all, proof and reasoning and, establishing new truths and results. And it was very different, but I liked it even more than I liked the previous stuff, which is kind of lucky, because it was sort of a bait and switch, but I ended up liking the switch better than the bait. So.
Right, yes. And one of my perspectives that sort of guides my overall research program, whether it be related to the collaboration between mathematicians and math educators or related to students' learning of proof, is this idea that teachers are sort of acting as these intermediaries between mathematics as a discipline and their students as learners. And I see them in this very important role of being able to provide an honest representation of the discipline of mathematics. And so that's why I'm really interested in teacher education and how we can bring more of what we understand the true nature of mathematics to be into the schools and providing that honest representation of the subject.
Absolutely. So we have kind of the general setting and topics. I was wondering if you could let us know the specific purpose that you're kind of setting out to achieve with this article.
So in the research, there is quite a bit of literature that tells us the strengths and weaknesses, misconceptions that students have in relation to constructing and validating mathematical proofs. As I was reading that literature as a doctoral student, I kept seeing throughout this idea in the implications section that we need instructional sequences that can help our students improve in these areas that we've identified. And that was coming up again and again in the literature that I was reading. So I said, well, okay, let's do that, and let's design an instructional sequence based on some of these findings that could help students sort of move forward. So that was how I started thinking about this research. So we were interested in determining, based on the instructional sequence that we designed, we were interested in determining, first of all, how the pre-service teachers, when they were validating students' written proofs, how their validations differed before and after the implementation of our activities. And we focused on validation rather than construction or some other element of proof, because as teachers, again, that skill in being able to read students' work and provide feedback and validate those arguments is really what we perceive to be an important factor for teachers.
Yeah, because these students, there's undergrad students at the time, but they're going to be teachers. So you're saying when they get to that teacher role, it's really about reading students' proofs and thinking through them and all the different dimensions of the proof.
Right. So that was the first element and sort of purpose for our study. And the second one, we wanted to know when our pre-service teachers were reading the samples of high school student proofs, what were the errors that they were attending to? And that gives us, again, a little bit more insight into how teachers perceive proof in general based on the feedback that they're providing and how they understand what it means to be a good mathematical argument. So we really looked at what were the errors that the teachers attended to while they were reading these samples of student work.
So can you tell us a little bit more about that sequence of activities? Just generally kind of what did it look like, or what were the characteristics of that sequence?
Sure. So the sequence of activities was designed primarily based on a review of the literature. So in the literature we found two major areas that students and teachers have had difficulty with in terms of validation of mathematical proof. One of those is the idea of, do we accept proof by example as a valid source of argumentation.
Right.
And so that's Harrell and Souder refer to that as the empirical inductive proof scheme. So we were interested in designing a sequence that helped students recognize that proof by example would not be sufficient as mathematical argumentation. So that was the one big element that we pulled from the literature and designed for the instructional sequence. The other is something that has been discussed in the literature, and we worked primarily from Annie and John Selden's work, where they found that students attend very often to the local aspects of an argument, and by that we sort of mean like line by line elements of a proof.
Can I find any error in this one line itself?
Yes.
Versus looking more holistically?
Right.
Yeah.
Right. Versus exactly the holistic, or what we called the global element of the argument itself. So we wanted to give, in this instructional sequence, students opportunities to read and validate arguments and think about the local elements, just line by line details, but also the global structure of arguments. So that was our intention with the instructional sequence, to think about those two big ideas and give students opportunities, time and space to be able to reflect on those ideas when actually engaged in validating proofs.
And so we know these students are prospective secondary mathematics teachers, but could you tell us a little bit more about who those students were and then what data you collected to then analyze?
So these students, most of them were in their final semester before their student teaching.
Okay.
And so these students had gone through their introduction to proof courses, much of their higher level mathematics courses. And so this course that they were in, where we conducted this study, was called Reading the Language of Mathematics. So actually in many universities, pre-service teachers may have a reading course, but it's sort of general.
Yeah.
It may be for all the science and English people are all together in that same course. But at USF, we were fortunate to have this class that Denise Thompson had designed on actually reading in mathematics.
Wow.
So we thought that would be an appropriate venue to add in this instructional sequence related to proof, as that's really closely tied to reading, of course, in mathematics.
And then I know you did kind of a survey with them before and after, or you had them actually look at some proofs, and then that's where you collect some data, or was there data in the middle as well?
Yes. So the data that we talk about in this manuscript is from the pre and the post assessment, and those came before and after the two classes where we implemented the instructional sequence.
Okay.
Both of the pre and the post assessment, we identified high school student arguments. These were authentic samples of high school student arguments that had similar errors. So in the pre-assessment, we would pick an argument from a high school student for a particular mathematical problem, and then we would try to identify another sample of a student's argument that had parallel errors in it. So our intention was to see, before the instructional sequence, what are some of the errors that the students are attending to? And then after the instructional sequence, what are some of the errors that our pre-service teachers are attending to? And how do they provide feedback to these students when they're actually writing to them? And so we asked them to read 6 arguments before the sequence, 6 arguments after the sequence, and they had to provide a numeric score, 1 to 4, where 4 was a very successful proof and 1 was completely unsuccessful argument. And then they had to provide a paragraph of feedback to the student.
Okay, and it was phrased that way, like write this as if you're giving it to a student who wrote that. Okay, great.
That's right. And another important thing is that they were told to identify the strengths and the weaknesses in the student's argument, and that actually, as researchers, provided us a lot more information about students' understandings, because as we'll talk about a little bit later, some of the students would emphasize strengths in the argument and say, this was a particular strength in the argument, but it ended up revealing to us that they were not understanding some of the aspects of the proof itself.
Yeah, as a researcher, if the student identifies something as a strength that's actually a flaw, then that gives you stronger evidence than if they just maybe mentioned it or failed to mention it as a weakness.
Right.
Wow. I'm speaking with Sarah Bleiler from Middle Tennessee State University about her article in JMTE entitled Providing Written Feedback on Students' Mathematical Arguments, Proof Validations of Prospective Secondary Mathematics Teachers. So I'm really curious then for you to tell us a little bit about what you found. What was it that the students attended to? How did they sort of interpret the errors or interpret what they saw in these student proofs?
Mm-hmm. Yeah, so when we originally looked at this data, we found that 100% of the validations for the 2 arguments out of the 6 in the pre and the post assessment that we as authors and researchers perceived to be valid, all of the pre-service teachers' validations of those arguments were correct.
Okay, so they could spot the correct, complete proofs.
That's right.
Okay.
Yes. But what was really interesting is when we dug into some of the data surrounding the invalid arguments. So 4 of the 6 in both the pre and the post assessment were invalid arguments. And so we found that pre and post, there were some arguments that the pre-service teachers seemed to be improving on in terms of their validation success as it is aligned with ours, and then some where they worsened. And so we really wanted to dig into that and see what were some of the potential reasons why their validations may have changed from pre to post, either in a good direction or in a bad direction. So one of the really interesting things that we found is that for one parallel set of pre and post arguments, so we had identified these as having similar errors. But what was different about them is the pre-argument was written in a narrative format. So the mode of argument representation was narrative, whereas in the post-assessment, it was written in a symbolic format by the high school student. And so when our teachers looked at these arguments, they would much more frequently identify errors in the narrative argument than they would in the symbolic argument. And so prior research has also shown that teachers and students may tend to accept symbolic arguments, right? And sort of believe that those are more valid as mathematical proofs than something that might be written in some other mode of argument.
Kind of seduced by the symbols.
Yes, exactly. That's right. So that was one interesting thing. So we thought, well, that may be a potential explanation for why their identification of errors in their feedback was not as high on the post-assessment, actually, as it was on the pre-assessment. Another thing, which was a positive, and we saw as a strength of our pre-service teacher population, is that they were able to identify when empirical arguments occurred and that those were not sufficient as mathematical proof. So a lot of times their feedback to the high school student would say, proof by example is not enough. And using examples is a great way to try to understand the problem or to come up with a conjecture, but it's not enough to justify, mathematically speaking. So that was really neat to see that they attended to that, and their feedback was very much focused on that idea. What happened, though, is that very often they would focus almost exclusively on that, and they may not provide feedback on some of the other errors in the arguments.
They would give that feedback and then they would stop when maybe some more feedback was needed.
Yes, yeah. And in some of the arguments, in one of the pairs of arguments, there was an expectation for the high school students in the directions of the statement of the problem that they prove by contradiction. And what we found is that our teachers, when they were reading these arguments, they would see that the high school student said, okay, I'm going to negate the conclusion of this proposition. And then what the high school student did was go through and actually, instead of using that negation to derive a contradiction, they then just started a direct proof and would work through the argument directly, and then at the end say, therefore, by contradiction.
So were they basically proving the contrapositive and kind of calling it like it was proof by contradiction?
They weren't even using contrapositive. No.
Okay.
For example, one of them, they would state the negation of the conclusion, and then they went through and used an actual proof by example, but in their case, they claimed it was a disproof by counterexample. Right? But really, it was only just an example, one example of satisfying the criteria of that argument. And so our teachers seemed to be satisfied by the framework that the high school students were using, in that they, negated the conclusion to the original proposition. At the end, they said that it was a proof by contradiction. They found a contradiction. But in the middle, if you're actually analyzing those high school student arguments, it's really just a direct argument or a direct example of how the statement would work. And so we found over and over again that the students would say things, and I'll read you a quote here. Okay, this student began correctly with stating the contradiction, but you need to use definitions to prove the statements. Okay, or the student starts off in the right direction by assuming that A plus B is rational, but the definitions the student provided for rational or irrational are incorrect. Another time they said, you understand the concept of contradiction, however, you need to be more explicit in writing and your use of definitions. So a lot of times they focused either on using definitions or on using symbols. That was their feedback focused on that idea, rather than on the actual big issue here was that the students were, in fact, not using proof by contradiction.
Yeah, and that's more at the global level of the proof.
Yes.
It's not actually doing that proof by contradiction. So I'm thinking back to what you mentioned about the research that you drew on about the empirically based reasoning, and that one seems like there was some successful, the students were fairly successful in recognizing that empirical arguments don't fully justify a statement. So that one seemed like you can kind of check that off. But then this one now is leading me to think, there's still some work to be done on gaining that global perspective, because these ones that you were just reading to me seem like, they're looking at some of the smaller features and not recognizing the problem with the global picture.
That's exactly right. Yes, they were really attending to those local details still, even after our instructional sequence. And so that seems to be something that's really lasting for these students. So we have thought about a couple ways that we might be able to address that, in future instruction. And one of the things that we thought would be helpful for the students is to actually go back to their validations and, in a sense, validate the validations, right? So as teachers, have them thinking about what is the feedback that we're providing to these students? What does that tell our students about mathematics? And what might we be missing here, right? What are some of the more global things that we might be missing? So that's one of the ideas that we thought could be interesting for future research as well.
Yeah, and I want you to speak a little bit more about some next steps. And so are there some other research directions that you think this article points to for the field, or are there certain questions that you are already wanting to tackle yourself personally?
Yes. So one of the things that we found is that students are attending, again, to these local elements and really to the structure of proofs. And they would find, for example, with the symbolic argument, they found much fewer errors in that argument, even though we, as the researchers, identified the same errors in the symbolic argument and in the narrative argument. And so we think it's important in the field for practitioners and for researchers to consider how we can give students more opportunities to see proofs in different modes of argument representation. And this is important, especially for teachers, because if they have a restricted view in terms of what counts as mathematical proof, then they may be less willing or a little bit more hesitant to engage students in proving at the K-12 level. So that's something that we think is really important, that teachers have more opportunity to see various formats of proof and understand that there are different ways that we can represent mathematics. And the important parts are these more global, logical issues.
Yeah, I always worry a little bit when there are teachers that really have a pet mode of representation, like they really want their students to use the 2-column format, or they really want their students to use the flowchart or whatever it is. I always get a little bit worried, because then I feel like if they really favor that mode, that it might really draw attention to the mode rather than to the actual logical argument or the actual mathematical ideas and the soundness of the reasoning. Mm-hmm. And to me, those latter things are where the attention should really be.
Yeah. Yeah, so another project that I'm working on currently, I'm working with Justin Boyle and Winnie Ko and Sean Yee, all of whom I met through actually the STAR program at AMTE. So we are working on a project where we're engaging our students, some of whom are pre-service math teachers, some of whom are just mathematics majors at the undergraduate level. We are engaging them in validating their peers' arguments and using those validations as a way to design a course rubric. So our goal there is that students begin to see mathematical proof as a negotiation process and something that happens within a community of practice. And so we're having them look at each other's arguments and then think about what are the characteristics here that are really helpful in terms of communicating the mathematical argument, and what are some of the things that maybe are not so helpful. And then in each of our 4 classes, we've had our students develop a rubric that they'll then use later in the semester as they go on and think about constructing proofs or validating other proofs.
Oh, very interesting. My guest is Sarah Bleiler from Middle Tennessee State University. And Sarah, I always have one last question that I ask my guests. Thank you so much, though, for talking about your article in JMTE. It's available online, as I mentioned, and it'll be coming out soon in the actual print version. But putting kind of work aside for a bit, I wanted to ask you, if you were not in math education, what do you think you'd be doing?
Good question, Sam. Let's see. I think if I were not in math education, which I can't even imagine not being, but if I were not, I would probably be a nutritionist. Yeah, so I'm really interested in nutrition and all the sort of different elements of cooking and just providing our bodies with good nutrition, and so that was probably something that I would be interested in. It's something I read a lot about, and I listen to lots of podcasts related to nutrition, so it's something that I have a passion for, and it might be something that I would have gotten into if I hadn't come to this math education wonderful profession.
Yeah, my mom, growing up, she always really emphasized well-rounded meals, and I was kind of like, But now I have my own little kids, and so now my wife and I all the time are like thinking, did you get enough vegetables today?
Yeah.
And, you know, it's really, it's important, really an important thing.
It is, yeah, it can make a huge difference also in just, you know, your ability to think about things, right, and be productive in work, so.
Yeah. Well, great. Sarah, thanks so much for being here with me.
Thank you. It's been a pleasure.
Thank you for listening to this episode of the Math Ed Podcast. If you'd like to support the podcast financially, please use the PayPal donation button at mathedpodcast.com.